All right, so here's another exciting episode of Advanced Level Chemistry. It is Tuesday, November the 18th. Wow, November 18th. This year is flying by. Okay. And if you're enjoying these videos, what are they supposed to do?
Subscribe.
And
Like.
hit that like button and hit that, ring that notification bell. All right, so here we go. Today we need to make sure that we kind of understand how to do everything. This is where the cloud of confusion is supposed to lift, and we're supposed to figure out everything that we need to know. Okay, you have a study guide, so you need to get out your notes and the study guide, and then we're going to kind of be looking at those and making sure that we know how to do all of these things. Okay? Today is going to be a day of understanding, if you put your mind to it. Okay? So we were trying to figure out, we have this whole pattern here of increasing energy. Now it's really important for us to understand this is an energy diagram, not a distance diagram. This is an increasing energy, meaning the lower energy, it's more tightly held to the nucleus. It takes more energy to release the electron, to free the electron. The electrons that are way up here, a higher energy, it takes less energy to remove them from the nucleus and make an ion. Okay? So that we're increasing energy, which means we're technically, most of the time we're getting farther away, but we saw that 3s, 3p, 3d are basically the same distance away. They're just held differently because they have different paths. So the S is always held more tightly than the electrons on the same energy level in the P than in the D. And then they actually begin overlapping. So we have to know how to do this overlap. What's the order of filling? Okay, well, there's 3 ways to learn that. Did I get to any of this yesterday? Okay, my 3 ways. I think we're right in the middle of it when the bell rang, I believe. Okay, so this is what we're talking about. There's good, bad, and ugly. The ugly is try to memorize it. Try to memorize that 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Okay, you're probably going to get messed up on that. That is the least recommended method of trying to know this. The second okay method, but still takes a lot of extra work, is this diagonal rule. Okay? And that's where it's on the very last page of your notes, and if you draw your diagonals, it goes 1s, and then you go from the head of the arrow back to the tail, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. That tells me the order of filling. But I really don't like having to write all that out. It takes up a lot of space. But, I mean, that works, and that's good, and that's an okay way to do it if you want to do it that way. But the best way is to use this amazing periodic table. Okay? So follow me over here. Keep following. Keep following. Really? You have all this up there? Mm-hmm. Okay. When we're looking at the periodic table, this is incredibly important. This is on the bottom. This is part of your study guide. If you want to kind of be using your study guide on this, turn to the 2nd page or 3rd page, wherever the periodic table is, bottom of the 2nd page. Okay? Because you're supposed to highlight the sections of the periodic table. So these first 2 columns, where are electrons going? Which sublevel are electrons going into in these first 2 columns? S. So that's the S block. The first 2 columns are your S. Okay? Then these 6 over here is which section? Electrons are going into which sublevel over here? P. So this is your P section. The electrons are going into the P sublevel. Inside the goalpost from 21 to 30, all this section in here, electrons are going into which sublevel? No. D. Okay? And then the bottom 2 rows down here, electrons are going into the F. Now there's so much that can be gleaned from that. Okay, so that's what you're supposed to mark down there on that. I mean, again, this is just for you to know, but I mean, that's what the periodic table's on there, just so you know which sections are the electrons going into which sublevels. Because that tells you so much about the electron configuration right there. Okay? Now, yeah, the yellow, your yellow is S, the green is going to be P, red would be D, bottom two rows is F. Okay? Now, when you go up now into the section above it, where in, what is it, like 12, or 17, I mean, through like 20, when it's asking about the different sublevels. First off, orbitals on the S sublevel are what shape? Spherical. Okay? Now, that's just you have to know. But then you go to the second question that says, okay, how many S orbitals are there on an energy level? Well, how many electrons can go into an orbital? Two. So I'm looking on my periodic table. So I'm 1, 2. The S section on the periodic table only has 2 columns, so only 2 electrons. So how many orbitals does that mean there can be? Again, how many electrons can go into an orbital? 2. So in the S sublevel, if I only have 2 electrons, how many orbitals must there be? 1. Right? Now, what's the first energy level that can have an S orbital? Well, we got hydrogen on the first row, and you should probably just know 1s. I mean, that just kind of sticks out. It just we kind of remember the 1s. S starts. That's the very first one we have. Hydrogen is number 1. That's the very first thing. So it starts. The S starts on the first energy level. Again, remember, helium technically could go there because it's 1s2. Okay. But because it acts as properties of the noble gases, they put it over here. But that's kind of what that gap right there is about, is where helium really should go. But it's got properties like this. So the first row is a little bit of an anomaly, a little bit different. Okay, but it's 1s2. Okay, so then we ask the question, how many electrons total can there be? Well, 2. And we know that because, well, 1, 2. We know that 1, 2. The S, you can only have 2 in the S. So then you go to the next question. Well, the P. Okay? Well, the shape of the P, we call it dumbbell. Right? That's dumb and bell put together. Well, but what's the first energy level that you can have a P sublevel on?
B. 2.
The second energy level. The second row is the first time we have a P block. Right? There's not one on the first energy level, but you have one on the second row, so the P can be on the second energy level. That's the lowest energy level. Now, how many orbitals? Well, I have 1, 2, 3, 4, 5, 6 electrons, so that's how many electrons total can be on the P. So how many orbitals must that be? 3. Because there's 2 electrons in every orbital. So you can deduce all of these questions, the answers to all these questions, just by looking at the periodic table and counting. Are you following me? I'm trying to get you where you don't have to memorize. You can just use the resource. You're always going to have a periodic table. You just use the resource. So then, okay, you come down to the D's. Now you have to remember, whatever row the D's are on, they're one behind because of that overlap. So on the 4th row, what D is this? 3D. So what's the first energy level that can have a D?
4.
No. 3. It's 3D. Even though it's on the 4th row, it's a 3D. Well, I'm skipped down. How many electrons total can be in the D? Well, I can't remember. We'll just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many orbitals are there? 5, because it's 2 in each. Okay? So obviously the same thing now down here.
What shape is D?
The shape of the D we say is rose petal, but that's all in your notes. Okay? That's just something you have to know. That's those fancy weird shapes there in front of Gabby. Okay? We just say rose petal. And then S, just so you know, are complex. But again, what do we know here? Here's 6S, and this is where these bump in the F's. What do we know? The D's are 1 behind, the F's are 2 behind. So it's 6S, but it's going to be 4F. So what's the first energy level that can have an F? The fourth. And again, remember, every time you go down, follow me, every time you go down an energy level, you get another sublevel. So you have 1 sublevel on the first, 2 on the second, 3 on the third, 4 on the fourth, and on the fifth, you do have 5, but it's that theoretical G that it mathematically is possible. But again, if an electron had enough energy to get into the 5G, it actually has enough energy to totally escape. The nucleus can't hold it. So they're theoretical there, but never occupied. That's why they don't have their own special letter. We just go alphabetical after that. But technically, every energy level has another sublevel. So 1 sublevels on the first, 2 sublevels on the second, 3 sublevels on the third, 4 on the fourth, 5 on the 5, 6 on the sixth. Okay? So you see how we can use the periodic table for all that? Okay. So now that we have that, how can we use the periodic table to get this order of filling? Well, we just follow along, follow the yellow brick road. Okay? So hydrogen has 1 electron, and it's going to be in the 1s. Helium, again, could be here, so it's 1s2. So, but my first energy level is filled. So then I go after 2, I go to 3. So I'm back here after 1s, I go to 2s. 2s1, 2s2. Well, where do I go next? Well, 4 goes to 5. So I jump across, and what section am I in now?
2P.
The P. So I go after 2s comes 2p. 2p1, 2, 3, 4, 5, 6. So now my 2p is filled. My second energy level is filled. So where do I go after 2p? Well, 10, I come back here to 11. Which section am I in on the periodic table?
3S.
I'm in the S, but I'm on the 3rd row, so it's 3s. 3s1, 3s2. So where do I go after that? Well, 12, I go to 13. Well, what section am I back in?
3P.
I'm in the P on the 3rd row, so it's 3p, 1, 2, 3, 4, 5, 6. So now my P sublevel is filled. So where do I go? 18, 19. Well, it seems like I should go 3, if I'm just trying to memorize 3p, I ought to go to 3d next. But I'm over here in what section?
4.
I'm in the S, so the S comes before the D. So this tells me the overlap. 4s1, 4s2. Now for the first time, I don't jump across the center section, I enter into the D zone. But D's are 1 behind, so it's 3D. So after 4s comes 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So after I get through the 3D10, where do I go next? Well, now I'm back in the P section, which is going to be the same as the row, so it's 4P. S's and P's are on the same row, whatever they are. So 4P, 1, 2, 3, 4, 5, 6. So 36, I go to 37. I'm back to what section? S. But now I'm 1, 2, 3, 4, 5S. 4D, 10. 5P, 6. 6S2. Now notice that we have the star and a big jump in numbers. So that means we jump down here. Into which section? The S, but they're 2 behind, so it's a 4F. So 4F, how many goes in the F? I don't know, I can't remember. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So how many orbitals are there? 7. So my 4F, 14. Then we come back here to 5D10, 6P6, 7S2, 5F. Now notice here, this is my last natural element. All of these other elements are all man-made, which means they just smash the nuclei together and make a new nucleus, but that nucleus is unstable, highly radioactive. It blows apart after a second or less, so they never have electron clouds. So we really never have to do this electron configuration for them. But if they had electrons, it would be 6D10, 7P6. And by the way, these are all named now. This is an old, and 118 is OG. Yeah. What? Is that what it is? I'm not sure why you would know that, but Oganescent, okay? You would think that One of these would be called one of the OGs, one of the originals, but this is OG here. Okay? Thank you, I'm here all day. Okay. All right, so do y'all understand? Do you see how the periodic table tells you that order of filling? Okay? So let's look at, so if I say I want to do an arrow diagram for arsenic, element number 33, okay? How many electrons is it going to have? Where are my last electrons going to end up at? 4p. 1, 2, 3, 4. So I'm in the 4p. How many electrons will it have in the 4p? 1, 2, 3. So I know I'm going to end on my arrow diagram on 4p3. So I'm only going to go to here. So when you draw an arrow diagram, you do not have to draw all the stuff above if you don't go to it. You only draw up to where you need. So that tells me, oh, I only need to draw up to 4p. I don't have to draw the whole thing. And then you want to know how does it go. And so then you just say, okay, well, I'm just going to follow, well, hydrogen, 1s2. And remember, so we have 3 rules. The Aufbau principle says I'm going to start at the lowest energy, so I'm going to go here and work my way up. I'm not going to put something up here without these being filled down here. Okay, this is the ground state. If you have electrons up here with empty spots in between, that's the excited state. That's how we make light. So this electricity is making those electrons jump from here up to here, but what do? They come back down, and when they come back down, that's when they're giving off photons, they're giving off light. Okay, but we force them up excited state, and then they naturally come down because everything wants to be in the lowest possible energy state. So when they come back down, they give off light in the form of EMR, photons and all that, which is the first page of the study guide. So we go hydrogen, helium, 1, 2. Then you go to lithium, 3, to beryllium, 4. Then we jump across and go to boron. Now remember Hund's rule. Hund's rule says you're going to put 1 into each before you begin pairing up. So you go 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10. Now I'm at the end of the second row. So now I'm going to arsenic. I want arsenic, element number 33. I know I'm going to stop here at 4p3. So I can just kind of keep going. Okay, but again, I just say, okay, so sodium and magnesium, that's 3s1, 3s2. Well, where do I go next? I go to aluminum, I'm back in 3p. Okay, aluminum 13, 14, 15, 16, 17, 18. Now I'm at argon at the end of the third row. So again, I'm trying to build, where do I go? 18, I go to 19, so what comes next?
Potassium.
Well, 4s, potassium. 19, 20, calcium. Now I enter into the D for the first time, calcium, so I go scandium to zinc. Now again, little tidbit. Hund's rule says you put 1 into each and begin pairing up. But is the 3D going to get filled? Yeah. So do you really have to go and then come back and fill up? I mean, you can just kind of go across since you know it's full. Okay? So I can just simply do this. Now, technically, we're putting 1 into each, but I'm just saying, look, I'm not going to know, nobody's going to know if you went and then came back, okay? You know it's going to be filled. But now I'm going to 4p. So how many go into 4p?
3.
3. This is where Hund's rule really has to make sure. Because you're not going to go 1, 2, 3. You're going to go 1, 2, 3. 1 into each. And they're all going to have, they can all be down or they can all be up.
But there's no way to tell whether we're down or up.
No, that's 50-50. Okay? So in a normal sample of arsenic, they're going to be evenly mixed. Okay? But you put it into a magnetic field and the magnetic field will separate them. Now the difference between arsenic and iron is that as soon as you take it out of the magnetic field, they just kind of meander back and remix. Iron, they stay separated. So iron stays magnetic where arsenic doesn't. Okay? So we all good with that? Super important to understand the periodic table. Now you can always do this. You can always do this one, but you just need to, the periodic table is so much easier and so much more amazing just to help me out on that. All right, but this still takes up a lot of space. Second to last page of your notes. Same thing, just different way of representing it. Electron configuration. Now, if you have it in your notes, the whole thing is written out. It's 1s2, 2s2. Again, you can memorize it. You can follow the yellow brick road. 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, and then 7s2, 5f14, 6d10, 7p6. Okay? That's a lot. Then that would be the electron configuration for OG, 118. That's 118. Okay? But let's just say I want to do arsenic, just like we just did right here. Arsenic is number 33. So where do I need to go to? Number 33, but where's the last electron's going to be? 4p. So I'm only going to have to go to here. Okay? Well, but I have to write the whole thing, but I'm going to say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Now notice the top. 2 and 2 is 4, plus 6 is 10, plus another 10 is 20, plus another 10 is 30, 33. The top numbers add up to the atomic number, the number of electrons. That's my electron configuration. It's shorter. The top number tells me the total number of electrons in that sublevel. We're not breaking it up into individual orbitals. But what if that's still a little bit too big to put on your periodic table? So we have this thing called, this is deep, stay with me here on this one, noble gas configuration. So what elements do you think we use in a noble gas? Hey, put your feet off the table. You're not at home. Come on, respect my stuff. You're not going to sit back and just prop your legs up. Sit up, take notes like everybody else. Okay? I'm really getting tired of the behavior back there. Okay? My patience is done. Okay? I need you just to start acting like everybody else in the room. Okay? I should probably edit that out. Probably won't. What was I saying?
Noble gas.
Noble gas configuration. Thank you very much. Noble gas configuration. Okay? Noble gas configuration. I even mentioned it coming in that we weren't going to do that, and you still sat back and just did it. Okay? That's the problem. Noble gas configuration. Again, what elements do you think we're going to use? Noble gases. Noble gases all have the filled S2P6. They all have that 8. That 8 you learned about in middle school. That magic number 8 of having, when things want to bond, they want to get that 8 electrons. Okay, we're going to talk about that next unit. Okay, so when I go and I look here, and if I see this, my previous noble gas is right here, my P6. That is going to be argon. Okay, 3P6 is argon. So arsenic has everything that argon has plus this much. So we're going to say argon plus 4s2, 3d10, 4p3. That's the noble gas configuration. You use the previous noble gas. Now, if you look on your periodic table, the one that matches up with this, you'll see that the noble gas configuration is given for every element right under the symbol. Now, there's several things that I don't like about the way they do it. Number one, they put all of the 3s together, all the 4s together. They don't put it here. They would say this one, the way your periodic table is going to do it is going to be argon, 3d10, 4s2, 4p3. Now, they're still going to follow the note, just a second. They're still going to follow the normal order of operation, the normal order of filling. They're going to fill the 4s before the 3d, but they write the 3d first. I don't like that. I want you to write it like this, in the order of filling. Yes, sir?
So if it was aluminum, would you do neon plus everything?
Yeah, aluminum is always going to be whatever it is. So everything on the third row is going to use neon. Everything on the fourth row is going to use argon. Everything on the fifth row is going to use krypton. Okay? So let's do this. Now, on your study guide, question number 20, what is that? 21. Let's just do sulfur right there. You want to draw an arrow diagram, electron configuration, noble gas configuration. See if you can just do that right there in your notes. And go ahead and pause that. The sulfur has how many electrons again? 16. Okay? So we're going to start at the bottom, doing the arrow diagram first. Okay? Again, you can do any one, but we're going to have 1, 2 in the S. 2, that's 4. Hund's rule, 5, 6, 7, 8, 9, 10, 11, 12. Now here, this is really super important. Hund's rule right here. This is, now when you're filling these other ones, it really doesn't matter, but when you get to the last one, you need to make sure 1, 2, 3, 4. Okay? Good. You need to have 2 unpaired, a paired and 2 unpaired. Okay? If you're going to get it right. This causes it to be affected by a magnetic field. That's how we know it's unpaired. Okay? So when I go and do electron configuration, I'm going to say 1s2, 2s2, 2p6, 3s2, 3p4. And notice that's going to add up to 16. So what's the nearest noble gas on the previous row? Neon. So my noble gas configuration is going to be neon, 3s2, 3p4. Okay? Now, you have 2 more on the study guide you can practice. You can pick any element. Any element. You got 92 choices. And you can draw electron configurations for them. You can draw noble gas configurations, draw arrow diagrams. Okay? So you can practice this as much as you want to. And just kind of see. I mean, and I'll check anything, but you should probably do the 2 on the study guide. You'll have time tomorrow in class. We're going to work on all this in class. Okay? We'll also talk tomorrow about the 4. I gave you 4 possible short answer questions as far as what would be valid answers on those. Okay? But one other thing that we need to talk about, and when we do this, I'm gonna go with lead. Where is lead's last 2 electrons gonna be? Lead is right here, number 82. Okay? So it's 1, 2, 3, 4, 5, 6 P, and how many in the 6P? 2 electrons. So if I'm doing the arrow diagrams, I gotta fill this up all the way. And I skipped over, but I'm gonna go fill that in. I gotta go all the way up to 6P. So this gets filled. I'm not doing them in the right order, I'm just filling it up. So I know where I'm stopping. So I'm going here. I'm going to here. I'm going to here. I gotta go all of these. Now again, where the Hund's rule says I should be putting 1 into each first, but I'm just trying to save time and fill in all my arrows. So now I'm going to go to 6P2. So here's Hund's rule. 1, 2. 6P2. It's not going to be paired up. It's going to be separate. Okay? Now, what I want you to know is that all of this is because of quantum numbers. Okay? All of this is because of Schrodinger's equations. This is the answers to all of Schrodinger's equations. We have this because of the quantum numbers.
So if like Einstein won the debate, then we wouldn't have to do all this stuff.
Yeah. Okay. Basically, yes. All right. Now, the Pauli exclusion principle says that you can only put 2 electrons into any orbital and they have to have opposite spins. But a corollary to that is he came out and said that no 2 electrons. We have 82 electrons here. No two of these electrons have the same exact 4 sets of quantum numbers. The quantum numbers being N, L, M sub L, and M sub S. Okay? So we have N, L, M sub L, and M sub S. And remember, this can be 0 up to N minus 1. This is minus L to plus L. This is either going to be plus 1/2 or minus 1/2. This is 1 to 7. Okay, so those are my possible values. So we have 82 choices here. All 82 have a different, it's kind of like a hotel room key. What floor, what sublevel, which specific orbital on that sublevel, and then which electron, the positive or the negative, the clockwise or counterclockwise, the up or the down arrow. Okay? So we have to go with that. So, okay, ladies, I'm going to let you pick. Ace, pick an energy level between 1 and 6.
3.
3. Okay? Pick a sublevel between S, P, and D. P. Pick. Okay, so we're at 6P. Okay, we're on, what did you say, 4? 4P.
I said 3.
3P. 3P. Okay? So now, what do we want to go? 1, 2, 3. What do we want to go? Where do we want to go here? Go here and up or down.
Up.
Okay? So we're going to pick, just randomly pick that arrow, that electron. So what would my 4 quantum numbers be? What would the room key be for that? Well, what energy level are they on? 3. We know that because it's 3P. The 3's telling me the energy level. Okay? Now, when n equals 3, L can equal 0, 1, and 2. Okay? What does that mean? Okay, on the 3rd energy level, how many sublevels do I have? 3. S, P, and D. This corresponds to the S, P, and D. Okay, so you're only allowed 3. Okay? Our electron that we're trying to figure out is on which one? P. So we're going to pick L equals, which one corresponds to the P sublevel? S, P, and D. L equals 0 corresponds to the S. L equals 1 corresponds to the P. L equals 2 corresponds to the D. Since our electron's in the P, we're going to choose which one of those 3 values. 1. Yes, sir.
I thought that there wasn't a D on the 3rd level.
No.
D is actually the 4th level.
No, D fills after 4S, but it's a 3D sublevel. 3D. Okay? So I'm going to pick L equals 1 because that corresponds to my P sublevel. Now when L equals 1, what can M sub L equal? -1, 0, and plus 1. Each one corresponds to a different orbital, a different orientation in space. So our electron's in which one? 0. And then is it going up or down? So we're going to say it's plus 1/2. So the code, the quantum code for that electron is 3, 1, 0 plus 1/2.
But the up or down's a guess.
What would this one be?
Down, but I thought we didn't know.
Well, this would, what would the new quantum numbers be for this one? 3, 1, 0, -1/2. Okay? 2 electrons in any orbital. Okay? So if I pick a different one. So if I pick this one right here. Okay? This is going to be electron number 2. This is number 1. What energy level is it on? 4. So what's N equal to?
4.
And if it's on the 4th energy level, it's a 4D. What is N going to equal? It doesn't matter. What number is in front of D? 4. So what energy level is it on? 4. Okay? If it's a 2p, what energy level is it on? 2. If it's a 6f, what energy level is it on? 6. Okay? Even though we don't have a 6f. Okay? It still would be. That's the energy level. So n equals 4. Now when n equals 4, L can equal, L equals 0, L equals 1, L equals 2, and L equals 3. Which one is our electron in? 2. Corresponding to the D. So L equals 2. Now when L equals 2, what can M sub L equal? Possible. -2, -1, 0, 1, and 2. Our electron's in which one? 2. And since it's going down, -1/2. This tells me the energy level. This tells me the sublevel, SP, D, or F. On each sublevel, we have different numbers of orbitals. This tells me the specific orbital it's in. Again, go into a hotel. Which floor am I going to? Which hallway am I going to go to? Which room on that hallway? And then there's only 2 in any room. Which energy level? Which sublevel? Which orbital on that sublevel? And then is it the up or the down? Okay? So if I was to give you then this one, where I would say, what electron is that? Don't say the answer, I'll just pick up what electron is that. Do what?
Valence electron.
No, it's not. Okay, Ace, which one?
It's the second one on 5S.
Okay, so how do we know that? So the 5 is telling me what? I'm asking you, Ace, go ahead and tell me.
The 5 is telling you that it's on energy level 5.
It's on the 5th energy level. Since it's at L is 0, it's telling me which sublevel?
This S.
S. L equals 0, always for an S. Okay? Now you only have one choice here for M sub L, it can only equal 0. And then because it's the down, we're picking that electron. Okay, let's just make sure we can do one more. Okay? We'll come over here. This will be electron number 4. Just see what you got. You already answered one. You guys spread the wealth. Do we have it? Okay, go ahead.
6.
6?
It's the number recorded.
This number. That is your N. It doesn't matter. They just the energy levels overlap. Why do they overlap? Because they have different times that they get close to the nucleus. Okay? That's still my energy level. 6. The energy levels. Now look, listen. This is important. You guys are all seeing this as a distance chart. This is not distance from the nucleus. Electrons on a 6th energy level, listen to me. Electrons on the 6th energy level are farther from the nucleus than electrons on the 5th and the 4th. This is an energy diagram. This is how tightly held the electron is. because they have different paths, these 4, 5, 6, 7 energy levels are all very tightly packed together. So there's not much distance between them. Because of the small but significant amount of time that the s electrons get closer to the nucleus, it's actually held more tightly than electrons on a 4f. So it fills first. Now, let's finish this. So what is the actual n value? 4. When it's 4, 0, 1, 2, and 3, S, P, D, and F, what sublevel is this one in? 3. Well, when L equals 3, minus 3, minus 2, minus 1, 0, 1, 2, and 3, our electrons in which one?
Minus 1.
Minus
Give me minus
1
1/2.
and minus 1/2. Okay? So we should be able to do this. Tomorrow is going to be all practice. So if you have any questions, tomorrow's the day to ask them. All right. Y'all have hey, we still have a minute to go, but no, we don't. Y'all go Jags. She's not paying attention. Hey. Well, I can't see where it is.